Hello, this is Sanu, and today we're going to continue learning about the machine learning process, continuing from the previous video. In the previous video, we've learned the basic overview of machine learning and a simple KNN method. Today, we'll discuss how we generalized our machine learning models outside the training set. The presentation slides and source codes I use here were obtained from the Intel Machine Learning course. I reorganized the contents for easy understanding. You can download the original content from the website using the link. Let's get started. A good machine learning model must generalize well to predict new unseen data. A linear model on the left, shown in blue, is too simple to represent the data and performs poorly on the new data. We call this the underfit model. The model in the middle is desirable but challenging to achieve. The complex model on the right performs perfectly during training, but it shows incorrect results when predicting. We call this the overfit model. In general, overfitting is worse than underfitting. Okay, let's find out how to fit our model to avoid these issues. Say, we have input data on movie information. To ensure the model generalizes to new situations, we split the data into two independent parts before training. One is usually larger than the other, say 70% versus 30%. The larger data set is the training data to fit the model, and the smaller data set is unseen data, test data, used when measuring the final error of the model. This figure shows the process of using training and test sets in scikit-learn, an open source machine learning library. Using the trained model, the predicted labels yPredict from test data are compared to the actual answers, such as yTest, to calculate the prediction error. The choice of error metric depends on the problem, and we'll cover this later. Cross-validation is a better way of generalization over a single train-test split. It splits the data into two parts, which we call training and validation data. However, we perform this split multiple times, and then we'll be averaging the resulting error. It takes more time. However, the performance measure is more statistically significant. We split the first into training data 1 and validation data 1. We repeat the split multiple times. The second validation set is composed of different data samples. Here, we can cross-validate the performance with the third validation data. This is the final cross-validation split. After the cross-validation, prediction errors are averaged out. We can do this for several models and choose the best one. Now let's move on to how to calculate classification and prediction errors. Here, choosing the right error measure depends on the problem. For example, a doctor wants to classify patients likely to get leukemia. In the training data, most patients are healthy, say 99%, and only 1% have leukemia. A higher accuracy is essential. However, if we build a model that always predicts healthy, it would yield 99% accuracy. In this imbalanced case, counting the number of correct classifications is often not the right measure, and more appropriate metrics should be used. To this end, we often use a confusion matrix that visualizes and summarizes the model's performance. The matrix's rows represent the actual answers in classes. The columns represent predicted labels. In binary classifications, 4 combinations of cells are reported: true positive, false negative, and true negative. For instance, a false positive is the number of incorrectly classified data as positive. The blue diagonal shows correctly predicted values. The most common measure, accuracy, is the proportion of all correct classifications. That is the sum of correct predictions, TP and TN, divided by the total results. It is straightforward but inappropriate and imbalanced data classification. Recall, or sensitivity in other words, measures the percentage of the actual positive data correctly predicted. It is defined as the ratio of true positive to true positive plus false negative. Suppose the number of actual leukemia data is 35, 10 plus 25, and the number of correctly predicted leukemia is 10. Then the recall is 10 over 35. Now, precision measures the percentage of all the predicted positives that are actually positive. It is defined as the ratio of true positive to true positive plus false positive. If a model predicts 15 data as leukemia, and 10 of them are actual leukemia, then the precision is 10 over 15. Specificity measures the proportion of all the actual negatives that were correctly predicted. In the leukemia problem, it means how correctly the healthy patients are predicted. Of the 65 healthy cases, 60 cases are correctly predicted. Then the specificity is 60 over 65. Now we've discussed 4 widely used error measures. Accuracy is a good measure for balanced datasets. Recall is proper when false negatives are more expensive than false positives. Precision is useful when the correct prediction of positive data is essential. The F1 score is a measure that combines precision and recall. It is defined as their harmonic mean. It represents how effectively the model captures the trade-off between precision and recall. The precision recall curve also visualizes the trade-off between precision and recall. It is a plot of precision, x at y-axis, and recall, x-axis, with the precision recall pairs obtained from different probability thresholds. This confusion matrix represents the 3-class classification problem. The blue diagonal is the model's accurate prediction. Accuracy is the ratio of this diagonal divided by the total results. Okay, that is all I prepared for this video. Thank you for listening and see you in the next video. Bye!